Here's the hard truth. You just spent 6 figures on an enterprise AI initiative. You picked the best foundation model, you've got a beautiful chatbot UI, and your CEO just asked it about last quarter's revenue, and it hallucinated a number that doesn't exist in any database you've ever owned. The model doesn't know your data, it was never trained on it, and that gap between what the model knows and what your enterprise needs it to know is the entire game. This is part 1 of a 5-part series where we go deep on every architecture pattern for giving LLMs access to your custom enterprise data, and we're starting with the most important one, the one you'll use 80% of the time, Retrieval-Augmented Generation, or RAG. Let's start with the fundamental problem. A foundation model like Claude or GPT-4 was trained on internet scale data. It knows a lot about the world, but it knows absolutely nothing about your internal wikis, your customer records, your SOPs, your compliance documents, or your proprietary research. You have 2 choices. Either bake that knowledge into the model, which means fine-tuning or pre-training, and we'll cover those in part 2, or you feed the model the right information at the right time, at query time. That's RAG. Here's the core idea. When a user asks a question, instead of just sending that question straight to the LLM, you first search your knowledge base for relevant documents. You pull back the most relevant chunks. You inject those chunks into the LLM's context window alongside the user's question, and the LLM generates an answer grounded in your actual data. The LLM becomes a reasoning engine. Your retrieval system becomes the knowledge engine, and they work together. Why does RAG dominate enterprise AI? 3 reasons. First, no retraining required. Your data changes daily. New policies, new products, new compliance rules. With RAG, you update the knowledge base, and the system immediately reflects the change. No GPU clusters, no training jobs, no model versioning headaches. Second, citations and traceability. The LLM can point back to the exact document it used. This is non-negotiable for regulated industries, financial services, healthcare, legal. You need to show your work. Third, data governance stays intact. Your data never enters the model's weights. It stays in your controlled storage, S3, your databases, your document management systems. You maintain full access control, encryption, and audit trails. A RAG system has 2 distinct pipelines, the offline ingestion pipeline where you prepare your data and the online query pipeline where you retrieve and generate. Let's walk through ingestion first. Step 1. Document loading. Your enterprise data lives everywhere. PDFs in S3, Confluence wikis, SharePoint docs, Slack threads, database records, API responses. The first step is getting all of this into a unified processing pipeline. On AWS, this typically starts with S3 as the landing zone. You can use AWS glue crawlers, Lambda functions triggered by S3 events, or step functions for complex multi-source ingestion. If you're using Bedrock knowledge bases, it natively supports S3, Confluence, SharePoint, Salesforce, and web crawlers. Step 2. Chunking, the most underestimated decision. This is where most RAG implementations go wrong. Chunking is how you break your documents into pieces that fit in the LLM's context window and can be individually retrieved. And your chunking strategy directly determines retrieval quality. Let me walk you through the options. Fixed size chunking. 512 to 1024 tokens with 10 to 20% overlap. Simple, fast, works as a starting point. But it's dumb. It'll split a paragraph mid-sentence, separate a question from its answer, cut a table in half. Recursive or semantic chunking. Split at natural boundaries, paragraphs, sections, heading levels. Respect the document structure. This is significantly better for most enterprise content. Parent-child chunking. This is the enterprise sweet spot. You create small chunks for retrieval precision, say 256 tokens, but when you retrieve a chunk, you return its parent context, the full section or page. Small chunks match queries better. Large parents give the LLM enough context to reason. Proposition-based chunking. The most advanced approach. You use an LLM to decompose text into atomic factual propositions before embedding. For example, let's take this statement. The company was founded in 2015 by John Smith in Austin, Texas. which becomes 3 separate propositions. Maximum retrieval precision, but higher ingestion cost. My recommendation for enterprise, start with recursive chunking at 512 tokens with 20% overlap. Measure retrieval quality, then move to parent-child if you're seeing context gaps, or proposition-based if you need maximum precision. Step 3. Embedding. Each chunk gets converted into a numerical vector and embedding that captures its semantic meaning. Similar content produces similar vectors, which is how retrieval works. Your embedding model choice matters. On AWS Bedrock, Amazon Titan Embeddings v2 is the native option. Supports up to 8K tokens, configurable dimensions from 256 to 1024, and it's cost-effective. Cohere Embed v3 on Bedrock is excellent for multilingual workloads. If you're self-hosting, the open source BGE and GTE models give you full control with no API dependency. Key decision: embedding dimensions. Higher dimensions capture more nuance but cost more in storage and compute. 1024 dimensions is the enterprise standard. For cost-sensitive, high-volume systems, 256 or 512 dimensions with Matryoshka models give you 80% of the quality at a fraction of the cost. Step 4. Indexing. Your vectors need a home. This is your vector store, and on AWS you have strong options. Amazon OpenSearch Serverless is the go-to for most Bedrock knowledge-based deployments. It supports KNN vector search plus BM25 keyword search in the same index, which enables hybrid search, and we'll talk about why that matters in a moment. Amazon Aurora PostgreSQL with pgvector is ideal when you want unified relational and vector queries. Same database, same access controls, same operational model your team already knows. Pinecone integrates natively with Bedrock knowledge bases and offers best-in-class metadata filtering. If you want full control and a self-hosted experience, then Weaviate, Qdrant, or Milvus on EKS give you maximum flexibility. Now the user asks a question. This is where naive RAG and advanced RAG diverge dramatically. Naive RAG, the baseline, embed the query, run a vector similarity search, return the top 5 or 10 chunks, stuff them in the prompt, send to the LLM, done. This works for demos. It fails in production. Here's why. The user asks, what's our policy on remote work for contractors in EMEA? The embedding captures the general topic, but it might retrieve chunks about employee remote work policy in North America, contractor onboarding procedures, and EMEA office locations. Related, but not the precise answer. Advanced RAG is what a production pipeline looks like. Stage 1, query processing. Before you search, improve the query. Query rewriting, use an LLM to rephrase the question for better retrieval. Query decomposition, break complex questions into subqueries. And HyDE, hypothetical document embeddings. Ask the LLM to generate a hypothetical answer, then embed that answer for retrieval. The hypothetical answer is closer in embedding space to the real document than the question is. This is a game changer for short, vague queries. Stage 2, hybrid search. Never rely on vector search alone. Combine semantic vector search with BM25 keyword search. Why? Vector search captures meaning. It knows automobile and car are related, but it struggles with exact matches. Product codes, policy numbers, acronyms. BM25 catches those. Combine both with reciprocal rank fusion and you get the best of both worlds. OpenSearch Serverless supports this natively. Single query, both search types, fused results. Stage 3, metadata filtering. Tag your chunks with metadata during ingestion. Document type, department, date, classification level, product line. At query time, filter before or after vector search. Show me engineering docs from the last 6 months becomes a metadata filter plus semantic search. Dramatically improves precision. Stage 4, re-ranking. Your initial retrieval returns, say, 20 candidates. A cross-encoder re-ranker, like Cohere re-rank on Bedrock, evaluates each candidate against the original query with much higher accuracy than embedding similarity alone. Re-rank to the top 5. This single step can improve answer quality by 15 to 30%. Stage 5, context assembly, and generation. Assemble the re-ranked chunks into a structured prompt with clear source attribution. Include instructions for the LLM to cite sources, acknowledge uncertainty, and stay grounded in the provided context. This is where Bedrock's Retrieve and Generate API handles it automatically, or you build custom prompt templates for your use case. RAG isn't one thing, it's a family of patterns. Let me walk you through the variants that matter for enterprise. Agentic RAG. The LLM doesn't just passively receive retrieval results. It actively decides what to search for, evaluates the quality of what it gets back, and iteratively refines its search. If the first retrieval doesn't answer the question, it reformulates and tries again. If it needs information from multiple knowledge bases, it routes queries to different sources. This is the pattern behind Bedrock agents with knowledge bases. The agent has access to retrieval as a tool, and it decides when and how to use it. Graph RAG. Combine a knowledge graph with traditional vector RAG. During ingestion, extract entities and relationships from your documents and build a graph. At query time, use the graph structure to find related entities, then retrieve associated document chunks. The power here is multi-hop reasoning. Who manages the team that built the feature that caused the outage last Thursday? A graph can traverse those relationships. Pure vector search cannot. On AWS, you'd combine Neptune Analytics for the graph with OpenSearch for vector search, self-RAG, and corrective RAG. The LLM evaluates its own retrieval results before generating. Are these documents actually relevant to the question? If not, it triggers a different search strategy, broader query, different knowledge base, or web search fallback. If the documents are partially relevant, it generates an answer but flags low confidence. This is critical for enterprise reliability. You don't want the system confidently answering from irrelevant documents. Self-RAG adds a quality gate. Modular RAG. Decompose your RAG system into independent swappable modules: routing, retrieval, re-ranking, compression, generation. Each module can be independently evaluated, optimized, and replaced. This is the architecture pattern for teams that want to continuously improve their RAG system based on production metrics. Let me give you two concrete AWS architectures. Option 1. Bedrock Knowledge Bases, the managed path. S3 as your document source. Bedrock Knowledge Bases handles chunking, embedding with Titan v2, and indexing into OpenSearch serverless, all managed. At query time, the Retrieve API handles hybrid search and metadata filtering. The Retrieve and Generate API adds the LLM generation step with automatic citation. You can have a production RAG system running in hours. This is where you start. Add Bedrock guardrails for PII redaction, content filtering, and topic blocking. Add Bedrock agents if you need the system to take actions, not just answer questions. Now, let's talk about the second option, and this is for the teams who hear managed service and immediately start twitching. I get it. Sometimes you need full control. Maybe you've got a very specific chunking strategy that Bedrock doesn't support. Maybe you're running a specialized embedding model that you trained yourself. Maybe you need to federate across 5 different data sources with custom re-ranking logic. Whatever the reason, you want to own every piece of the pipeline. Fair enough. Let's build it. So here's how this typically comes together on AWS. Your documents are sitting in S3, right? You set up step functions to orchestrate the whole ingestion workflow. When a new document lands in S3, it kicks off the pipeline. Lambda functions pick it up and handle the chunking, and this is where you get to go wild. Recursive chunking, proposition-based, parent-child, whatever your evaluation data tells you works best for your specific documents. You're writing that logic. You own it. Next, those chunks need to get embedded. Instead of being locked into Titan embeddings, you spin up a SageMaker endpoint running whatever model you want. Maybe it's a fine-tuned BGE model. Maybe it's Voyage AI for your legal documents. Your call. For storage, you've got options. OpenSearch if you want that hybrid keyword plus vector search capability. Aurora with pgvector if your team already lives in the PostgreSQL world and you want to keep everything in one place. And then the query side, This is where it gets really interesting. You build a custom orchestration layer, could be Lambda, could be a service running on ECS, and this thing handles all the advanced query processing we talked about earlier. HyDE for better retrieval on vague queries, query decomposition for complex multi-part questions, hybrid search across your index, cross-encoder re-ranking to surface the best results, and finally context assembly before it all goes to Bedrock for generation. Now, I'm not going to sugarcoat this. This is significantly more engineering effort. You're building and maintaining every component. You're handling the scaling, the monitoring, the failure modes. But here's the trade-off. And for some teams, it's absolutely worth it. You control every single decision point in the pipeline, every chunking boundary, every embedding dimension, every re-ranking threshold. And when something isn't working, you know exactly where to look and exactly what to change. Now, evaluation, the part everyone skips. This is the most important part of this entire series. You cannot improve what you don't measure. Measure retrieval quality. Precision at K, recall at K, mean reciprocal rank. Are you retrieving the right documents? Measure generation quality. Faithfulness, is the answer grounded in the retrieved context? Relevance, does it answer the question? Hallucination rate, is it making things up? Use frameworks like Ragas for automated evaluation. Build a golden test set of 100 or more question-answer pairs with known source documents. Run evaluation on every pipeline change. Track cost per query, embedding cost, search cost, LLM generation cost, total end-to-end. You need this for ROI conversations. Let me leave you with the essential takeaways. RAG is your default architecture for enterprise LLM systems. Start here. It's the fastest path to production, it handles dynamic data, and it keeps your data governance intact. Don't stop at naive RAG. Hybrid search, re-ranking, and query processing are the difference between a demo and a production system. Chunking strategy is your highest leverage optimization. Invest time here before tuning anything else. Evaluation is not optional. Build it from day one. Measure retrieval and generation quality continuously. In part 2, we're going deep on fine-tuning and pre-training. When RAG isn't enough and you need the knowledge baked into the model itself. We'll cover LoRa, CLoRa, full fine-tuning, continued pre-training, and exactly when each approach is worth the investment. I'll see you there.